Very good day to the beloved panels. My name is Chen. Today I am going to present my final year projects, where the title is CFD Analysis on the Aerodynamics Characteristics of Small Size Car Vehicles Under the Influence of Steady Crosswind. The supervisor of my final year project is Dr. Izwan Amin bin Ishaq. The content of this presentation will be includes abstract, introductions, literature reviews, methodologies, result and discussion, conclusion, as well as the reference. In the part of abstract, the major concern is the crosswind. Crosswind eventually will give the effects of the vehicles where it causes the unbalance and it will cause the vehicles to deviate from the path. Hence, it will cause the yaw angles. In this project, it is a numerical approach where the ANSYS software is the platform to execute the simulations. The crosswind yaw angles will be varied from 0 degree up to 90 degree. The incompressible flow surrounding the vehicles is solved by Reynolds equation conjunction with the K epsilon turbulence model. The Reynold number have two types, which are low and high Reynold number. The Reynold number depends on the velocity of the vehicle. As a result, since it's concerned about a crosswind, hence the aerodynamic loads, whereby the crosswind yaw angle increase, it will cause the side coefficient to be increased as well. But when the crosswind yaw angle increase to 60 degree, there is a slightly drop on the side coefficient. In flow structure, when the crosswind yaw angle increase, the vortex bubble formation is getting larger on the leeward side. Lastly, there is no significant difference to be compared in the aerodynamic loads with the high Reynold number and low Reynold number. The crosswind basically is under the family of unsafe operation because it's concerned about the environment factors. The crosswind eventually will have the more impact to the vehicle compared to headwind and tailwind. So the crosswind stability's attention is about the vehicle motion and dynamic response under the influence of crosswind. This impact will become more significant to the vehicles that have a large surface frontal area and high center of gravity. Overturning and side stick are actually the consequences of crosswind. The aerodynamic of the vehicles becomes more important factors than to be considered. Different segmentation of car eventually will result different aerodynamic characteristics. High energy losses and the decrease in the vehicle performance have resulted from the faster acceleration of the vehicle systems. This will have a greater impact when the automobile is traveling at high speed under the influence of crosswind. The research objective first is to analyze the aerodynamic loads of moving vehicles under the influence of steady crosswind. Second is to investigate the flow behavior and its characteristics of moving vehicle under the influence of steady crosswind. Lastly, is to compare the quantitative aerodynamics characteristic between the low and high Reynold numbers when vehicle is moving in a steady crosswind. These are the literature reviews that have been used for me to conduct or completing the research. For example, the Saleh papers help me in defining the geometrical modeling. So I have also used another journals that for me to understand what is the flow separation and what is the stagnation point, and when the streamline hits the vehicles, how it occur, how is the flow separations, and where is the high pressure region and low pressure region. And last but not least, is the Meili studies where the armored vehicles model that have been used to study the effects of the crosswind at various yaw angle. In the methodology parts, so the first step is the research start, whereby to get the general idea of this research, what is going on or about. Then after that, after have a clear mind, then we have to define the objective and the scope. Then we will go for literature review to get the theory and get to know some past investigation that related to our research. Then we will go for the geometrical modeling, where the vehicle model that we chosen for this study is a vehicle from segment A. and the configurations or the dimension of vehicle that had been shown in the slide below. Okay, then after that we'll go for a numerical simulation setup in ANSYS software. After that we will try to testing or run the ANSYS simulation. After that we will go for the validation. If the validation is not successful, eventually we need to go back the numerical simulation setup to make the amendment or to correct the mistakes or the error that presents in the numerical simulation setup. So basically here comes to a loop between the numerical simulation setup and the validation. So if the validation is success, then we will go for a real case simulation, where this is the outcome of the research. So based on the result that we obtain, we need to discuss and make a conclusion of this research. And lastly, here comes to the end of the research. So the most important in the methodology that need to take note is the size of the enclosure. First is the size of the enclosure. The size of the enclosure is should be ideal size enough so that it doesn't affect the result of the velocity streamline and the vorticity. So the velocity, if the size enclosure is not big enough or ideal enough, eventually the vorticity or the velocity streamline it will affect it, whereby the velocity streamline or the velocity, we cannot see the formation of the vorticity and the velocity streamline. We cannot see the vortex form or even the recirculating formation bubble. Next will be the boundaries conditions. The boundaries condition is whereby we need to define which area is referred to which detail, such as the outlet or inlet, crosswind outlet, wall, and the vehicle surface. This is very important. So next one is about the grid independent test, where this is the validation. So the grid independent test is an important requirement in the early stage of developing a competent numerical approach was determining an acceptable grid structure with numerical boundaries conditions and a turbulence models for numerical simulations. So based on the result of the grid independent test, eventually we can observe that at the number of nodes of 661,406, the grid coefficients achieve a constant value whereby it is 0.29. So this meshing is using a high quality mesh, and the number of nodes of 661,456 will be applied for the real case simulation. In the result and the discussion, the first factor will be emphasized on the aerodynamic loads. So eventually we can see that no matter in the drag coefficients, lift coefficients, and even all the side coefficients against the yaw angles, both Reynolds number actually behave the same way, where increase, both Reynolds number also increase, decrease, both Reynolds number also decrease as well. So let's take a look at the drag coefficient. So eventually we can see that there is a significant drop in the range of 30° crosswind angle up to 60° crosswind yaw angle. This situation will be happens basically because the high pressure that exerted on the frontal surface of the vehicle will be decreased, since the due to the crosswind effects, it will cause the wind to be migrate. So it will give a less impact to the frontal surface of the vehicle. So this is the main reason that it will cause a significant drop in drag coefficients. Next will be the lift coefficients. Eventually we can see that both Reynolds number having the increased trend, and for the crosswind yaw angles below 45° crosswind yaw angles, eventually it's a low crosswind yaw angles. Eventually we can see that the crosswind yaw angles still able to create a downforce which provide a stability to vehicles. So as the crosswind yaw angle approaching or getting higher up to 90°, eventually the lift coefficients have a positive value, which will alter the lift, and hence it will cause the overturning to be more favorable. Lastly will be the side coefficients. So obviously we can see that when the crosswind yaw angle increase, the side coefficient also increase as well. Since there is no significant difference between the high and low Reynolds number in terms of aerodynamic loads, hence in the flow structure, the high Reynolds numbers will be projected. This is because there's a high possibilities for the high Reynolds numbers to occur the accidents, and the vehicles travel in high Reynolds number, eventually it will cause the unstable and deviate more from a path that it desired to travel. So in terms of pressure contour that's superimposed with the velocity streamline, eventually it can be analyzed that the pressure contour at the crosswind 0° yaw angle, the high pressure region is exerted on the frontal surface of the vehicles. So as the crosswind yaw angle increase, the high pressure region has slowly migrated to the windward regions, while for low pressure regions it only appears at its side and the edge of the vehicles. In terms of velocity streamline, it can be analyzed that when the crosswind yaw angle at 0°, there is no vortex formed at the leeward region and the windward regions. The vortex forms at the rear side of the vehicles. This is because there is a flow separation occurs, and when the velocity streamline hits the frontal surface of the vehicles, it actually known as a stagnation point. Besides, as the crosswind yaw angle increase, eventually we can see that the vortex streamline bubble forms is getting larger. In pressure contour on vehicle surface, the high pressure region has slowly migrated to the windward area, which is totally the same as the pressure contour, while the low pressure region it forms more at the leeward side edge of the vehicles, and this situation happens for the low crosswind yaw angles. When the crosswind yaw angle approaching higher, eventually the low pressure regions actually disappears from the leeward regions and appear slowly from the rear to the front of the side at the windward region. In the vorticity point of view, we can see that when the crosswind yaw angle is 0°, we can see that this recirculation formation of bubbles is appear on the rear side of the vehicles. As the crosswind yaw angle increase, it can be observed that, or it can be analyzed that the circulation formation of bubbles is more side to the leeward region, and besides that, from the leeward region we can also observe that or analyze that the vortex bubbles is getting larger and larger. As a result, at the crosswind yaw angle of 90°, we can see that there are lots of large vortex bubble formed at the leeward region. In conclusion, in the aspect of crosswind, all aerodynamic quantitative and qualitative equities exert a significant influence on the vehicle's dynamics behaviors. According to the results, the drag coefficients occurs a significant drops in the range of 30 up to 60° crosswind yaw angles. So when there is a positive value of lift coefficient, eventually it will give the vehicles the lift effects and alters the overturning to be occur. In the term of side coefficients, as the crosswind yaw angle increase, the side coefficient also increase as well. But there is a slightly drop at the 60° crosswind yaw angles. In terms of flow structures, the pressure contour and the velocity streamlines, the high pressures move to the windward area and the vortex bubble lines getting larger as the crosswind yaw angle increase. In the pressure contour of the vehicle surface, the high pressure regions is slowly migrated to the windward regions, while the low pressure regions appears at the edge of the vehicle. So, and in the vorticity viewpoint, we can see that the vortex bubble formation form is getting larger, and the tail of the recirculating formation is more side to the leeward region as the crosswind yaw angle increase. So the reference for below is the reference that I've been referred in completing my research. That's all from me. Thank you.